for the introduction. Can you hear me okay back there? Awesome, all right. Well, the objective here is to talk about safeguarding robots that are doing arc welding. How many of you are involved in that type of application? Okay, so I'm going to cover it in a number of topics. I'm going to talk about standards and regulations that apply that you have to meet. Then I'm going to talk about selecting the safeguarding, which involves risk assessment. And then I will talk about some typical solutions that are out there and how that's done in the industry today. And then I'll wrap it up with some new technology that's come out so that you can consider that in your applications to further your productivity. Okay, first of all, what regulations are necessary? When we're talking about North America, of course, we have OSHA, that's the law of the land, right? So here are the most common regulations from OSHA that apply to robotics. I didn't cover hygiene, and here you talk about it all day long, and I didn't cover that. But this is specifically in safeguarding. In Canada, if you have installations or experiences in Canada, then there are some corresponding regulations there. And more so in the province of Ontario, that's their industrial belt. Now, in Europe, there's the directives. How many of you heard of the machinery directive? Okay, well then not too many of you are dealing with Europe then, I guess. This is similar to OSHA, except that it's pointed towards who is building the machines, who's providing the machines. And if you make your own, then it applies to you. But those same regulations are used by the users also through their occupational laws that each country will have, which I don't have listed here. But okay, so when we're talking about the regulations before, they were pretty general. You know, guard the point of operation, guard the power transmission. And when you look at robotics, it's, well, how does it apply? I guess in a general sense. But the good thing is that there are also standards in the different countries, in the different regions. And what we have in a standard is basically what we think is the best practice. So when you're looking at a particular type of machine, you're going to say, hey, how should I do this? And you look towards standards. Standards should be written geared towards the requirements of the regulations. So here in North America, the standards we look at are ANSI standards. So how many of you look through or read or get a hold of ANSI standards, right? Okay, that's what it's all about. There's what we call is a sponsoring organization that's recognized by OSHA and by local authorities, which would be people like building inspectors in the different communities, and they will recognize a document that is published by ANSI. So when I'm looking at equipment, I want to look at what standards are published by ANSI that apply to my situation. In Canada, it's CSA. In Europe, it's CEN. And internationally, it's ISO and IEC. Sometimes it's worthwhile looking at some standards of other countries if something particular isn't covered in a North American standard. But now let's talk about robotics specifically. If I'm doing a robot cell, there's different things to look at. First of all, there's a classification of standards that are general. You know, if you're using a robot, here are the requirements, or I should say, not requirements, but the voluntary best practice that the industry has recognized. So if you look here, there we go. First of all, I've got the international standard, EN ISO 10218, covers the safety requirements for robot cells. In America, in the US, ANSI R1506 gives general requirements for safeguarding a robot, and Canada has their own, Z434. But now, since I'm doing specifically arc welding with a robot, then I want to look at what is the specific standard that applies to that. And we're fortunate here in the US that we do have a specific group of standards that apply there, and they're sponsored by published by ANSI and sponsored by the American Welding Society, and it's the D16 series of standards. The most critical ones I list there that I see. Of course, there's a fourth one I should have listed, right, Vern? But we have D16.1 that gives specific requirements for safeguarding arc welding systems. Point 2 talks about the installation requirements and component requirements for the cell. And point 3 talks about a risk assessment. How do I do it? Because if you look in D16.1, it says do a risk assessment, and it refers you to D16.3. And I'll talk about those. But here's the basis for how I should safeguard a robot cell. It's in the applicable standard that's published by ANSI that is specific to my application. So now, as I said, each one in the industry is pretty much set now that you need to do a risk assessment. In the 3 standards that I listed out there, 2 of them, or 1 of them requires a risk assessment, the international one. The US one and the Canadian one have prescribed methods and risk assessment methods, and they're evolving. And the trend in the industry is to do a risk assessment. Now, as I said, we're on the topic of risk assessment. And the other standards point towards doing a risk assessment, the general standards, and the specific D16.3 standard from the AWS also defines a risk assessment methodology. So I will talk about risk assessment in a general sense, and then specifically the prescribed strategy selection, as I call it, risk assessment methodology. That's my interpretation of what's in there. It defines the strategy to safeguard a robot based on the concept of risk assessment. So let's look at risk assessment in a general case first. Risk assessment in machinery is defined as a risk level that is based on 2 factors. First of all, what's the chance that I'm going to get hurt? And you saw similar concepts when we looked at the fire risk assessment that we looked at. What's the chance that something may happen that is bad? And weigh that against the severity, or how bad might it be. Are we talking about a fatality, or are we talking about a broken finger? So if you look at this model, it says that the risk has to be related to both of those. So if I have a robot cell and I predict through my probability estimations that I might end up with a small finger fracture, say once in 10 years, I might say that perhaps that's tolerable. I'd rather it not be. But at some point, I might say it's not worth spending $500,000 to upgrade the cell. But if during that same period of time, for the same probability, once in 10 years, it may be an amputation, then obviously that is too high. Then you have to do something. You either have to invest or you have to replace. So the concept of risk is that it's not only the chance of getting hurt, it has to be weighed against what is that severity of injury. So there's a number of tools that will guide you through a risk assessment. This is the basic model that's out in the industry. If I have a robot cell and I need to determine what my risk sources are and how I have to lower them, I go through a procedure somewhat described in this flow chart. I don't have enough time to go through specific examples, but I wanted to introduce you to the basic concept. On a risk assessment, we decide what the limits are of a risk assessment. What is this? It's an arc welding cell, and I'm going to be welding a certain type of material at a certain rate, generating a certain amount of fumes and a certain amount of productivity, piece rate. And so my risk assessment is going to be based on that design. If the cell gets changed, then I have to relook at, am I creating new hazards and new risk sources? Then I have to decide, okay, what can hurt me on that? I will look at, most specifically, there's a robot in there and the robot could smack me, right? So that's the biggest hazard. But then there's the voltages that are present, there's the hot surfaces, the arcs that are being created, the sparks flying out, the ergonomic issues of lifting parts and loading cells. So I look at what are the hazards, and then I have to estimate the risk level based on the chance of being injured by that particular risk hazard, either being hit by the robot or my finger getting crushed in the clamps that are clamping the part in place in the weld fixture. All of those I have to estimate, and then I have to evaluate them based on what our society thinks are low enough risk levels, and that's where methodologies help us out. But I decide, are my risk sources there low enough, and if they're not, then I have to take steps to lower them. How do you lower risk sources? Well, I'll go through that, but primarily we think about safeguarding as the most common avenue to reduce a risk source. So, okay, so there is a number of methodologies. All the standards point towards doing a risk assessment, but all of them are very clear that we don't mandate one particular methodology. It is left up to the integrator and to the user to determine which methodology fits their environment. Which one am I most comfortable with? I have two examples here. The first one here is the one that I use at Hills. It's a numerical system where I look at the degree of harm, how badly might I get hurt, compared against the chance of getting hurt, which is estimated by looking at three factors. What's the chance of something, some hazardous situation occurring, whether it's the failure of the control system or misuse by the operator? What's the chance of avoiding a hazard, depending on how quickly it develops? And how often am I exposed to that? How often am I entering in to change or clean a weld tip in that cell? So those factors are weighted, and when they're multiplied to give me a level, and that number, whether it's 0.1 or 500, relates to what would be considered a risk level. And then the methodology would provide a recommendation based on the risk level, whether you're operating in an unacceptable area of risk where you have to do something, if you're operating in an acceptable level of risk where you say, okay, I'm done, or something that you might consider a decision point, whether you can tolerate it or if you have to, or there's a way to lower it. So the methodology allows you to predict where you're at on the risk level and guides you to what should be done. And all the three methodologies I'm presenting here would do that. Now, the second one is a common one used in North America. That is a matrix that's defined in the current R1506 standard. And it's a little simpler than the method I described before, but it's the same concept. I'm going to look at the severity of injury, whether it's high or low. I'm going to look at two additional risk factors that relate to the probability of being injured, exposure and avoidance. Come up with a risk level. You can see here basically high severity, high exposure, potential for avoidance leads me to an R2A risk level. And then the methodology says, well, if you're an R2A, if you are at an R2A risk level, then you need to implement engineering controls at a control reliable circuit, which would be a dual channel type circuit. So the methodology allows you to estimate the risk level and then guide you towards what you should do. So we talked about two different We talked about two methodologies. Now we're going to look at, before I go into the third one, I want to talk about where we are right now, because there's different ways of safeguarding the system. I'm going to talk about the more general, more complex way to approach it, and then I'll look at the more specific arc welding method. But I think it's important to know both, because there'll be times when you need both. So when we go through a risk assessment and we decide that we have a risk source that we have to reduce, I don't want someone to lose a finger every 10 years. I have to do something. What do? There are three ways to reduce risk. And in all methodologies, it talks about these concepts, and I want to present those here. So first of all, the best way to reduce a risk is to eliminate the hazard. So as we were seeing here with the fuel extraction, if I can adjust my process and eliminate the production of high levels of particulate or of toxic materials in the air, then that's the best way to reduce the risk versus having to wear a respirator. Same concept here. I'll show some examples. The second way to reduce risk is the one we most commonly think of. That's the safeguard to cell. Put a fence around it. That will take care of it. Now you can't get to it. The third way to reduce risk is through administrative controls, procedures, training, signs, warning lights, rails. And then finally, as part of that administrative control, you also have PPE. Sometimes, you know, it's a hot part that you're unloading from the fixture. You've got to wear gloves. There's not much way around that. So what we look at in a risk assessment, the outcome is, how am I going to reduce it? Here are my choices. So let's look at some examples here. Now, risk reduction by safe design. Here are just some simple examples of that. And you have to do this if you have the ability to redesign the cell. You don't always have that ability. Now up here, I have some rollers, and the rollers would cause a nip point. So in the machine, if I could design a machine so that the material can go in through a little hole and I can't reach that hazard, then the hazard isn't there to have to safeguard. Another thing here is I have these rollers that are moving a web of material, textile or paper, and so this is called an S-turn. So I have one roller that's rotating this way and the other rotating that way. And if they were close enough and I could get my hand in there, it could grab my hand. So I just separate them. I'll move them apart. So now, if I stick my hand between the rollers, they're not going to grab my hand. I've eliminated the hazard by redesigning the machine. Finally, down here, if I have a conveyor and I have rollers spinning, if this roller here was powered and driving, my hand could get caught here between the moving surface of the roller and the fixed surface of the machine. I can design it to make this an idle roll in a slot that pops out should I get my hand in that area. Here it wouldn't pull me in, and if I had my hand here, getting pulled in, the roller would pop out. So sometimes you don't have to safeguard a hazard, you redesign the machine to eliminate the hazard. Unfortunately, if you have a robot cell, it's not a good idea to eliminate the robot because you won't get anything done, right? So that's not always a possibility. Now, another common way to reduce by design is substitution. So in a situation here, I have a robot doing work and I have a person that has to enter within the reach of the robot to load a part into a fixture. So here I have the problem that I have a robot that could injure the person. How do I safeguard it? One possibility is substitution. Let's say I put a shuttle in now to feed the part so that the person is not exposed to the robot, he's exposed to a shuttle. Shuttle being a little simpler machine, I can guard it easier. I reduce the risk by substituting a lower hazard source compared to the original design. So reduction by elimination or substitution. Now obviously you can't do that for everything, so you're going to come down to having a safeguard, and the most common safeguard is a fixed or movable guard. So I would bolt a plate in front of the gears so you can't get to it. Or I might, if I have to go into, say, the robot cell, I put a fence around it and I can interlock gates so I can open the gate. And when the gate opens, the switch opens and it stops the robot. So guards, either fixed or interlocked. Presence sensing devices. You'll see down there some examples of robots, and then most of them have light curtains in front of them. Why do they use light curtains? Well, the nice thing about a light curtain is it's not going to slow you down when you approach the robot. You don't have to stop to open a door. You just walk through into the beams. The beams detect the person and shut down the robot, or shut down the turntable, which is the most common application out there. So where I have frequent access, then I want to look at presence sensing. And that will protect me from the hazard. Now, a fence and an interlock's a whole lot cheaper, but if you're running parts and the operator's going in there every 3 minutes, you're going to improve your productivity if he doesn't have to stop to open the door. So they might cost more, but they'll benefit you in the right applications. In addition, there's also some other things where you might have to do. Here is a two-hand control. There are applications where you load a part and you have to hold both hands on the controls and protect your hands. The robots out there have enable switches so that when I go inside to program it, I have to hold a switch so that If I get in trouble and I let go of the switch on the teach pendant, the robot will stop. That's a way of reducing the chance of me getting injured by the robot. Now finally, in terms of hardware devices, you have complementary devices, and the most common is an emergency stop. I would expect that any robot cell or any other major piece of equipment in your facility will have a means to emergency stop the cell or the machine. It's going to be a red button, and if it's up to current standards, it's going to have a yellow background. And when I push that, everything has to come to a safe state as fast as possible without causing any other problems. So, on any of those robot cells out there, you look around, you'll find the emergency stops, which is a requirement in some applicable standards. Now, we talked about, okay, I went through a risk assessment, I identified what the risks are, and I lowered them through one of three ways. Now I think it's a good time to look at the protocol method that's in the AWS D16.3. It is a risk assessment methodology because it provides a selection of a safeguarding strategy based on severity and a probability of injury, same as the others have. But it's boiled down to robot arc welding. So first of all, the probability of injury occurring. If we look at what's the chance of me getting injured, this methodology looks at a concept called class, the class of the cell. And that's defined by the speed of the robot, the amount of pinch points that may be in the hazard, and how tight of a cell is it, and what type of control you have over all the different hazards, whether it's single point of control or multiple areas of control. So first of all, it looks at probability of the injury. Secondly, it says, well, how badly might it get hurt? And in this, because for the most part, arc welding robots are a particular style, and they have been a particular style of manipulating robots for many years. This standard was based on the fact that we know roughly what kind of robot. If we look at how big the robot is, then we could look at how badly, we can make an estimate of how badly it might hurt us based on its size. So it's going to be so what it does is it takes these two factors on your cell and it gives you a strategy. Now, so it's simple, but be aware that no standard stands on its own. If I'm designing a system and I want to be compliant, there's not one standard out there right now that's going to give me all the answers. This is going to be my starting point for arc welding, but there's going to be certain things that I need to look at other ones on, so be cautious there. It's simpler, but it's not all the answers. So in the protocol method, like I said before, you look at both factors. Number one, you say, hey, what kind of robot is it? Is it a high energy robot, medium energy robot, low energy robot? Essentially, that comes down to primarily its payload. But it also talks about the potential speed that it might run. But primarily, it's the payload. If I have a robot that's 3 kilograms or less, one of the small tabletop or one that's the minimum size arc welding robot, that's 7 pounds. If I have a small robot, then we're going to classify that as a low energy robot. It means that when it smacks you, it's going to hurt you, but it may not kill you, okay? It's going to be less. Now, a medium energy robot is going to go from 3 to 15 kilograms, and obviously it's going to hurt you more if it hits you at the same speed or in the same situation. And then finally, a high energy robot, something that's over 15 kilograms. So we're talking some beef to that robot. So in that situation, it is expected it's going to be a very serious injury. So those are weighted. So you see here, I have protocols. Depending on the energy level of the robot, the protocol numbers are going to go up. The highest being 1, the most stringent being 1, the least stringent being 4. But there's a second axis. It says, what's the chance I'm going to get hurt? And here it says, given the basic cell of the robot for arc welding, what conditions in that might promote injury or promote avoidance of an injury? And it comes down to the speeds that you're running the cells, the types of congestion within that cell, how many pinch points, how far apart are things from each other, and what kind of control do I have over the movements when I'm exposed to that robot. So if we look at it, class number 1 says there's a lot of things working against me, that promote the chance of you being hurt. And if that's the situation, and I don't have a high energy robot, I have to go to protocol 1. We'll talk about protocol. Protocol is a strategy for safeguarding that's the most stringent. Now, as I go down in classes, if I go down to class 3, meaning I have a better chance of avoiding an injury, and I go down to a low energy robot, it drops down to a protocol 4. Still a strategy to protect me from that robot, but less stringent. So let's see what those strategies tell me. If I look at strategies, they're called protocols, and there's 4 levels. Protocol 1 being the most stringent, protocol 2 removing some of the requirements, protocol 3 removing further requirements, and protocol 4 being the minimum you have to do on a arc welding robot in North America. So let's look at specifically, what's it telling me? Protocol 1. I'm going to tell you guys, most of the time I think you're going to be in protocol 3 or 4, but you know, you might, whoops, is that me? That's me. It's time for my Bible study. I'm going to miss it this week, so let's just say no. Okay, so we look at that, and if I have a high energy robot, and I have a situation where I have a high potential for being hit by that robot when I'm exposed to it, I have to do 1, 2, 3, 4, 5, 6 different things in terms of my strategy. So number 1, I have to have ingress and egress barriers. That's a fancy way of saying fences around the robot. Okay, I have to have fences around the robots, and if I have a way in, I have to interlock that gate or put a presence sensing device in. So that I have to guard around the perimeter of the robot. Number 2, I have to provide a way of energy isolation. Oh, by the way, OSHA says you got to do that anyway, so it's a bit redundant. I have to have alternative procedures for regular servicing. In a robot cell, like any machine, there are times you have to go in there and do some things. You have to clean the tips, you have to replace the hoses, you have to tweak the program. Some of these are considered out of the ordinary routine, so you have to go through lockout, tagout, or possibly robot teaching mode. Some things are considered minor, like regularly changing the tech, in which case you can define that here as it's called regular servicing and provide a different way of protecting a person. You'll see out there in some of those cells, when I open the interlock, I have a way of putting my own personal safety lock on that door so it doesn't close behind me. Therefore, as long as I have my lock on there, and I'm the only one with the key, that robot's not going to run. So I give myself a way of going in and protecting myself for this minor servicing. Now, the next thing I have to do with that is I have to have a single teach pendant and a single programmer. I can't have 2 people in there, just 1. If I need a spotter, then he's going to have to spot from the outside of the cell. I have to have mechanical hard stops to restrict the reach of that robot. I have to minimize how far it can reach. I don't want it to hit the barriers. I don't want it to go any place it doesn't have to go. So I need to restrict that in a qualified way. And then finally, I have to protect from all environmental hazards. That's pretty much a given too. I better have fume ventilation capture. I better have wall curtains around it. If I have people in the area that might get exposed to that. So here is a cookbook on how to safeguard an arc welding robot in an American standard. Doesn't give me all the answers, but it gives me the high level where to start. So let's look at a basic cell. Now this is an arc welding cell, a bit more complicated than some of the ones down there, but as you can see, I have a robot here. Let's see, where's that robot? Robot's right here. And there is a positioner. A very common situation is to provide a positioner for the robot, and typically 2 stations, so that I can load a part on one station while the robot works behind a barrier on the other station. And the positioner has means to manipulate that part, rotate it around so the robot can reach all the areas it has to weld. And so that's a pretty common application out there. So someone would come in through a barrier to load this side while the robot works on this side. I don't cover hygiene and ventilation. That would be on top of all I have here. But you can see I have a barrier around the side, and there is an access gate to go in the program. And I have a system out here to protect people from going in to the, and be exposed to the rotating positioner. So here are the steps, the way I look at them when I'm looking at a robot cell and I have to guard it. Number one, you have to safeguard the perimeter. Got to have a fence, and I got to go in, so I better interlock the gate where I go in. Number two, I have to look at where the operators are exposed who are loading this machine. Some robot cells are fed automatically, but most of them in arc welding, it's a person that's going to be bringing this heavy weldment and locating it in front of the robot. So where he comes in contact with the cell, I have to protect him in some manner. Most common is presence sensing devices, but you can do it other ways. Number three, I have to allow for energy isolation. And not only the main electrical lockout, I have to lock out air, I have to lock out gas supplies, I have to block gravity's loads if necessary. If I have a positioner that raises way up high, and I need a way to block it up in that position, because I'm assuming at some point I'll have to service it up there. Number four, I have to consider this alternative protection for minor servicing. Again, there'll be times you want to go in and you don't want to lock the cell out. You want to go in there in 5 minutes and get back out. So you want to give somebody a way to do that. Number five, you have to look at the circuit integrity. I have an interlock guard. Is it a single channel circuit? Is it a dual channel circuit? How do I do it right? You have to cross that bridge. Number six, I have to look at the process. So obviously at a minimum I'm going to have ventilation and welding flash filtering. Okay, arc welding, I'm going to put a fence around it, so the best bet is to put a fence and hang your curtains off of that fence and take care of perimeter and the weld flash. So you can see here the typical application. I'll have a presence sensing device to detect me when I go inside here that protects me while I'm here, while the robot works on the other side of the barrier. When I go into a cell, and you can see here is an application where this switch here, when I open the gate, those two different devices come apart. I lose the signal, I shut down the robot. In order to run the robot, those two sensors have to come together so I can lock it out here. And I can put my lock on so that they don't come into contact and they can't start the cell. So I would use this to go in to change the tip, to unjam the part, to clear out some debris that commonly collects. A minor thing. And when I'm looking at where the operator is going to load, basic, most common solutions are a light curtain or a laser scanner. Now, laser scanners are great, but you have to be careful of the particulate and the fumes that you're going to generate in a robot arc welding cell, but they do a great job. Now, when you put a presence sensing device in, like I said, the D16.3 doesn't give you all the answers. If I put in a presence sensing device, there's a thing called safe distance. You have to comply with the safe distance formula. B1119, I should have put that up there, provides that information. And how do I determine how far away this light curtain should be from the hazard? So it's not just nailing it. As someone said at a conference once, you're not supposed to use the most convenient mounting surface rule. You're supposed to use the safe distance rule. Energy isolation, of course, you're going to have a means to lock things out and a procedure to go with it. So you want to make sure you provide a lockout procedure along with your cell. And on the safety circuits, you're going to have a circuit that's going to read the interlock on the gate, go through some kind of logic system, whether it's a programmable system or a relay, knock out contactors that knock out power to motors. Now, the current methodology is to describe the circuit in terms of single channel or dual channel, and the most common terminology is categories, category 1, 2, 3, or 4. And a chart like this would be used by your controls engineer in conjunction with you on the risk assessment to determine what category is necessary. The categories, there's actually 5 of them. You can see that we start with single channel systems and we progress up to dual channel systems. Essentially what we're trying to do is improve the reliability of the system, because everything you build may fail. We want to try to make it fail in a safe state. The new concept's going to be performance levels, and there's a lot of discussion in the industry on that, but I want you to be aware that there is a movement towards performance levels, and not to be caught off guard if you're having someone design a cell and this issue comes up. At the same token, we look at severity, exposure, and possibility of avoidance to determine a risk level and the appropriate reliability of the circuit rated in a performance level. Basically, the higher the risk, the higher my circuit reliability should be, because I don't want that circuit to fail at the same time I'm in a position to be struck by the load. Emergency stop, of course you need your emergency stop. That's going to be that nice red button with the yellow background, or maybe a pull cord. And you're going to supplement everything with awareness beams. So you might have rails, you might have horns, and definitely warning signs. Now to finally supplement that, you're going to have train people how to run that correctly. Sometimes there's things you have to do where you can't safeguard it. You may have to have job safety analysis to determine how to do something safely if you're working in the cell without the safeguards. And obviously keep everybody up to date in terms of their training. Finally, you have to remember, what do I have to specify for protective, personal protective equipment? I mean, that's already an OSHA requirement, and you want to include that in terms of the design of the cell. Do I need gloves? In addition to the standard eyeglasses, safety shoes, and earplugs. So in certain situations, you might wear sleeves if you're handling a lot of sheet metal. Now, one thing I wanted to talk about is certifications. When you're starting to move into robotic arc welding and you're having a lot of exposure to that, a lot of different machines, there are two certifications that are available. Number one, if you're going to buy a system from somebody, I would ask them if they're certified. The AWS has a crawl certification where it defines if the integrator has personnel that are familiar with the basic requirements to run a robot arc welding cell, and you want to have your own people who are also certified. In addition, the RIA has a certification for an integrator that confirms that they do know the standards and that they can integrate a cell and as part of their experience, though they can show experience in quality and responsiveness and proper documentation. So if I was buying a robot cell today, I'd ask them, hey, do you have crawl certified specialists within your organization, and are you certified by the RIA? So these are things that help a user better ensure that they have proper systems being delivered. Finally, I want to finish up with new technology. One of the big things that technology has done for us in robotics is it's made use of new concepts out there in terms of trying to make our job for safeguarding easier. One big thing is software limits that are safety rated. Any of those robots out there, I can define how far it can go out before it has to stop. But typically they're not safety rated. But the concept is out there, and technology is out there, and the suppliers of robots do have that available. And it's going to help you in terms of making the cell safer, less requirements on safeguarding, and make the cell smaller. So when you're specifying a robot cell from somebody, hey, what can you do for me in terms of the safety-rated space limits? Well, one important thing that we have out there, if you look at plasma arc, you don't want the robot to misposition that torch out towards the cell and cut through the glue, right? So there is new technology here in defining where that robot can go, where there would be a monitoring system that would shut it down should it start going in a direction that would cause a problem. Now finally, there's collaborative robot operation. There's situations where we can eliminate fixturing, we can bring a robot in closer proximity with people, work closer with them, where the robots have monitoring built in that is safety rated, that would ensure that the robot is going to stop when necessary before it might harm someone. In a safe standstill application, the robot here is allowed to move into an area where the person can approach it, and as the person approaches within the reach of the robot comes to a stop, but still has the capability of moving, but is monitored. So you could have people load the robot directly versus have a fixture where the robot will pick it up. There's also applications in welding where you have the robot guided, where you come up to the robot, grab a control stick, and move the robot. But you actually touch the robot and guide it to where you want it to go. In applications where you're welding big parts, where fixturing the part still doesn't give you complete information as to where the part is, this could be used to help eliminate some of the variation in the process. Safe speed and distance monitoring. The technology is now allowing us also to develop systems where the robot can operate without a fence in certain areas. And should a person approach, the robot would avoid that person. Finally, collaborative operation with force-limited applications. Robots are now being implemented such that they don't have guarding around them, but they're designed so that they can't exert a force or contact pressure that would lead to higher than a bruise. So the robots now can be implemented without a guard, and Vern loves that. I'm sure he'll be one of the first to implement them. And
No,
I say that facetiously.
I'm going to put myself in harm's way for the next robot show. My wife says don't kill yourself, but I'm going to take myself out.
But anyways, the technology is there to open up to new applications that we have, and I'm interested to see where it might lead in the welding process. Okay, there we go.
Thank you very much.
Thank you for your time.
Do you have any questions?